Hello everyone. In this video, we're going to complete some exercises related to hyperbolic functions. The first examples is find the derivative of the functions y equal x squared plus 9 times hyperbolic cotangent x over 4. So for a function like this, we see that we have the form of u v. If you want to know the derivative of u times v, it's going to be u prime v plus v prime u. Now, in these two functions, we can identify the first factor as u and the second factor as v. Now, if we said that u equal x squared plus 9, then u prime would be 2x, okay? And if we set v equal hyperbolic cotangent x over 4, now we want to know when you take the derivative of a hyperbolic function, for cotangent, what you're going to get. First of all, I need to remind you that if you take the derivative of a hyperbolic functions cotangent, u, the derivative is a hyperbolic cosecant square u times u prime. Now, in the cotangent, hyperbolic cotangent x over 4, let's say u in this case is 1/4 of x. So u prime would be simply 1/4. Now, if we go here, we know that the derivative of hyperbolic cotangent x over 4 would be equal to cosecant, hyperbolic cosecant square times x over 4 multiplied by 1/4. Now we can come back here and say that the derivative of a such function would be equal to, there is a negative. Let me add the negative because in this one we have a negative. So everything here is negative. So that would be negative 1/4 of cosecant, hyperbolic cosecant square times x over 4. Now we can go and because the access to find derivative of y, so y prime, remember it's u prime v plus v prime u. So what is the derivative of u? The derivative of u is 2x times v cotangent, hyperbolic cotangent x over 4 plus v prime u. In this case, we know v prime u would be plus negative 1/4 hyperbolic cosecant square of x over 4 times u. U is x squared plus 9. So we can rewrite this one because we cannot simplify. We can conclude that the answer is 2x hyperbolic cotangent x over 4. Now we have minus 1/4 of x squared plus 9 times cosecant. Let's write cosecant clearly. Okay, we have cosecant, hyperbolic cosecant square x over 4. So this is the derivative of the function y. We need to always remember that there is a list of formulas that involve the differentiation and integration of inverse hyperbolic functions or simply hyperbolic functions. We're going to continue with another examples where they ask us to find the indefinite integral using the formulas from the theorem regarding differentiation and integrations involving inverse hyperbolic functions. So we need to remember to use absolute values where appropriate. We use C for the concept of integration. You know, when we don't have the limits, I mean the boundaries AB, then this for the indefinite integral, we need to always add a C. Let's say that in this example, we see that we can rewrite that functions as x over 3 square minus x square power 2 dx. Now, anytime we have those type of functions, our goal is to identify what part is A, which is 3, and what part is U. You see, U here is x squared. So if we take the derivative of U, that would give us 2x dx. But because we already see that we have x dx in this part, so we can replace it by U. Now, what we can do is to multiply both sides by 1/2. So we're going to have 1/2 du equal x dx. Now, we have one term that would replace a, that would replace u, and that would replace 1/2 of du. Now, let's put everything together because we know that x dx over 3 square minus x square power 2, we can rewrite it as, because now we know what is x dx is 1/2 of x, 1/2 of du over a square minus u square. Now, we know when we have a square minus u square, we can bring the 1/2 in the front. So it would give us du over a square minus u square. Now, something we need to remember is from all the formulas we have, if we have du over a square minus u square, we can replace it by 1 over 2a ln a minus u over a plus u plus c. Remember, we said to use the absolute value when it's appropriate. In some other examples, it can be also equal to arctangent. We can also use arctangent for it. So for example, this one can be equal to 1 over a arc hyperbolic tangent u over a plus c. But in this particular example, we're going to use the part where we said ln. Let me change the color so we can see it. Now, remember, we know what is a, so it would be 1/2. I'm going to keep the 1/2 out. And then we would have 1 over 2a ln a minus u, okay, over a plus u. So we're going to have a plus u plus c. Now, because we know what is a, we can replace 1 over 2 times 3, okay? Ln, now we know what is a is 3 minus x squared over 3 plus x squared plus c. When we multiply and also distribute the 1/2, it's going to give us 1 over 2 times 3 is 6. 6 times 2 is 12. Ln 3 minus x squared over 3 plus x squared plus c. This is the final answer. So we can continue to do more examples involving either hyperbolic functions or just finding the indefinite integral. In this example, they ask us to find the indefinite integral. You see, for the concept of integration, as I said, anytime we uh, look for the indefinite integral, we need to add the constant c of integrations. In these examples, we see that we have some formulas that says if you have du over u square root of a square minus u square, and we could use that one. But our problem, we look, if we set u equal ln x, we end up not having u outside of the root. So we cannot use this property. So we need to think of something else. Now, when I see that examples, I see also that I can rewrite it as 3 over square roots of 9 minus ln x power 2. I can bring the 1x over here. So that's still the same thing. Now, if we set u, we know a, we can set a equal 3. I don't know if you can see that. Let's remove the 9. I can simply say that 9 is 3 square. So a is 3, u is ln x. Do you know what is du? If u is ln x, what would be du? Yes, that would be 1 over x dx. Wow. All right. Now you see, for this part right here, we can consider it as du. Now, taking our 3, let's put the 3 outside. As we said, having the 3 over square roots of 3 square minus ln x power 2 1 over x dx. We can bring the 3 outside, okay? So, and then we said that we have square roots of a square minus u square, because 1 over x dx is du. Good. Now, we know also that from some formulas we already covered, that if we have du over square roots of a square minus u square, this formula gives us arc sinus u over a plus c. Now we can substitute 3, okay, du over square root of a square minus u square. That would give us 3 arc, because the 3 is already there. It's not included in the formula. The 3 is a constant, so I jump it in front of the integral symbol, and that would be u over a plus c. Now, because I know what is u, I can substitute u is ln x over a, which is 3 plus c. Okay. We can continue doing another examples. When we look at the examples of find the integral, the indefinite integral, we're gonna continue using the C for concept of integration. In some examples, we could split and give each of the term their own denominators. We could simply write it as x over square roots of 64 minus x minus 8 square plus dx, of course. We could have 9 over square roots of 64 minus x minus its squared dx. But our problem, look at the first one. While the second one is possible, but for the first one, we have an x in the denominator that we won't be able to do anything with it. So unfortunately, we cannot use this property to distribute, to split the denominator. So we need to come up with a different strategy. One of the strategy you probably could remember, there is one formula that says if, I'm sorry for that, it doesn't give me enough. Okay, so we have u over square roots of a square minus u squared du. If you have something like that, it would simply be equal to square roots of a square minus u square. Now we see if for any chance we can transform that expressions to show that we have u over square root of a square minus u squared, then it's gonna save our life. So what we're going to do is to take the x plus 9 we have up here, and with the square roots of 8 square minus x minus 8 square dx. What I'm going to do is to rewrite it as x plus 9, keep it as is, square roots of 8 square minus x minus 8 square. Now, I want to show I can have the term x minus 8 in the numerator. So what I'm going to do is to subtract 8 and add 8. So by subtracting 8 and add 8, you see that I can have x minus 8, and I have also 9 plus 8. Remember, 8 minus 8 doesn't change anything because it's like 0, but it's very important for me to show that I will have a u over square root of a square minus u square. So the term in the denominator stay as is, dx. Now, we can rewrite it as x minus 8 plus 17 over 8 square minus x minus 8 dx. Now, we can distribute. We can have a first term with x minus 8 over square roots of 8 square minus x minus 8 square dx, plus we can have 17 over 8 square minus 8 square dx. Some other formulas you need to remember here, we just said also, if you have, I'm going to use a different color to show you this. If we have, you know, a square, let's say for this one, let me continue with red first. We're going to have x minus 8 over square roots of 8 square minus x minus 8 squared dx. Let's bring the 17 outside. So we simply have dx over square roots of 8 square minus x minus 8 square. Now, we know that if we have for this term, for this one right here, du over square roots of a square minus u square give us arc sinus u over a plus c. And we know also for something like this one, okay, we can have u du over square roots of a square minus u square. We can also have negative square root of a square minus u square. Now, all we need to do is to show that we have a square. As you know, a is 3, u is x minus 8, so du is simply equal to dx. Now, you see from these expressions, we know for the first one, it would be u du over square root of a square minus u square plus 17 dx over du. Sorry, we need to add du because dx is du. So we're going to have du over square root of a square minus u square. So what we end up having is negative square root of a square minus u square for the first term plus 17. So we can erase those because you know what are those for now. I can erase those so because you see what are those. Okay, so we can have plus 17 arc sinus u over a plus c. So when we replace everything, we're gonna have square roots of 64 minus x minus 8 square plus 17 arc sinus x minus 8 over 8 plus c. So we can leave the answer like this, or you can also change, you know, x square. Remember, if you have x square, x minus 8 square, this can be x square minus 16x plus 64. Now, because we have a 64 here, you know, a 64 minus 64 would be equal to 0. So remember, we can leave it like this, or you can continue to simplify. One more example to complete. We see here also that's a very simple one where we can rewrite it as dx over 4 square minus 3x square. So if we set u equal to 3x, you know du would be equal to 3 dx. So one third of du would be equal to dx. So we know by what we should replace the numerator. And we also know that a equal to 4. Now, if we rewrite everything like dx over 4 square minus 3x power 2, we know that dx is 1/3 of du over square roots, not square roots, we don't have any square roots. We have only a square because a is 4 minus u square because u is 3x. Now we can bring the 1/3 out, du over a square minus u square. In the previous examples, so in the first examples, we said that du over a square minus u square would be equal to arc. Okay, we can have it as either using the ln. We can either use ln or we use the arc sinus. All right, so that's what we're gonna do in this case. So we're going to use the arc tangent or with it. So it gives us 1 over a arc hyperbolic tangent u over a plus c. So when we see this one, we said that we have a 1/3 outside, 1 over a, which is 1 over a arc hyperbolic tangent u over a plus c. But we know what is a and u. So 1/3, 1 over 4 arc inverse hyperbolic tangent. When we said arc hyperbolic, it can be also inverse. I mean, tan power -1. You can write it like this also. U is 3x over 4 plus c. So final answer would be 1 over 12 arc hyperbolic tangent 3x over 4 plus c. This is the final answer. So hope these 5 different examples on how to find the indefinite integral of functions involving either inverse or hyperbolic functions. You can use them to do more. Have a good day. Enjoy these exercises. Hope you subscribe for more video. Take care.